Thank you for that introduction. Yes, I'll be talking about cluster cosmology constraints that we obtained from DES using a new simulation-based forward modeling technique that I've developed in collaboration with these people that I've listed below. Okay, so to begin, these are constraints on sigma and omega m from Planck in black and from DES year 1, 3x2 in green. For those who don't know, 3x2 refers to three 2-point functions: cosmic shear, galaxy clustering, and galaxy-galaxy lensing. So this is a fairly standard probe now for low redshift clustering. And so you can see that the 3x2 in green is roughly in consistency with Planck, with maybe a hint of assay tension. This is what you get when you apply a standard approach of cluster cosmology to DES clusters identified from the same exact imaging that produced the green contour. So when this was obtained, people immediately decided that it was completely implausible. You're in 5.6 sigma tension with Planck, and even you have roughly 2.5 sigma tension internal to DES, right? So the exact same imaging data is producing these blue constraints and these green constraints. And so when I say a standard approach, I'm referring to sort of the Halo model approach, where you explicitly parameterize the mass observable relation, and then you convolve with the mass function to get the abundances, and then you have some model of the lensing profile based on NFW, most likely, to do calibration in the mass observable relation. Right? So this result was deemed to most likely be the impact of selection effects. And so this is what happens when we apply our new forward modeling methodology. Right? So we've shifted into agreement with 3x2, which is what we expect. We still have some hint of assay tension with Planck, but at least it's not totally implausible, right? And we've also improved in our precision relative to the standard approach. So I will tell you about how we achieve this. The basic idea is that we're attempting to forward model the selection of the clusters in simulation-based models. So this is a process to produce a cluster selection. First, you generate a mod galaxy catalog. In our case, we use HOD methodology. We assign richnesses / cylinder counts based on a weighted count of the mod galaxies within cylinders centered on the clusters. So this is motivated by the fact that we know that optical cluster selection is finding overdensities of galaxies with photo-Z's, and so you have some redshift kernel and some aperture at the location of each cluster. We then select based on abundance matching, which I will describe further in the next slide. And then at that point, you have a cluster catalog in your mod, so you can compute whatever 2-point function. In this case, we're looking at the lensing and the abundances, so we cross-correlate with simulation particles. Okay, so one word on abundance matching. So in what I've described, we're not making the assumption that this weighted count in cylinders is identical to the richness. First of all, this is an unnecessary complication, basically. So we only need to know what halos / clusters enter which bin so that we can compute the lensing. So we instead assume that rather than being able to predict the absolute value of the richness, we can predict the ranking with minimum scatter between the true richness and the thing that we measure in the simulations. And then we just do abundance matching to produce the samples. So we match the counts, right, given the assumed cosmology at the point on training set. So then the last thing that needs to be described is that we are using emulation to speed this entire process up. So what I've described in the past 2 slides takes about 20 minutes per HOD plus cosmology. And so that's not tractable for inference. So we speed it up with the simplest thing, Gaussian process. It works quite well. So here we're looking at the lensing profile of our training data or the data itself. So the data is points with error bars. You can see that we've generated a training data set that spans the plausible range of the actual data in the universe. So this is DES year 1. This is a single redshift bin with points color-coded by richness. And then on the right-hand side, I'm just showing you the accuracy of the emulator. So this is the leave one out emulator accuracy. You basically omit a single cosmology, all the training sets associated with that cosmology, compute the emulator, predict the data that you left out. And so that's what this is, relative to the error bars in DS, which we calculate analytically. So that's what the shaded regions are. So in short, we are subdominant relative to the errors in the data. So we can use this for inference. Right? Okay. So once we do this, we send that emulator through MCMC. We marginalize over various nuisance parameters having to do with miscentering and baryon effects and photoses, and so we get this red contour. And so we are significantly improved in precision relative to the standard method. So this is both because we're using full shape information of the lensing profiles rather than sort of compressing it down into a weak lensing mass. We also have a more efficient, just in terms of nuisance parameter space, model of the selection. And finally, the selection effects, which have some cosmological dependence, now become a source of signal rather than just something that is systematic you have to worry about. And the last aspect of this is that we also are pushing down to lower richness. So I think that was mentioned in the talk earlier this week that in the original Y1 cluster analysis, you could bring the blue contour into rough agreement with Planck and 3x2 by throwing out the richness 20 to 30 clusters. So by doing that, you are removing the plurality of your data. We are able to, with this forward modeling methodology, go down not only to richness 20 and 30, but all the way down to richness 10 and 14. So this is another part of where we are getting such improved constraints from. Okay, so we do various robustness tests. So each one of these panels is showing a test to just probe the robustness of our method. So here we've split the data into disjoint richness bins and redone the inference. So here we've done the same except for redshift bins rather, and here we split by scales. So the overall picture here is that everything appears to be consistent. So we're confident that our results are robust. And here I show comparison with other constraints from the literature. So on the left-hand side, this is not an exhaustive representation of the literature. These are the chains that I was able to obtain. But here we have other optical cluster analyses. So KIDS, HSC cross, or SDSS clusters cross HSC lensing, and then reanalysis of DES, but omitting the large scales and including cross correlations in purple. And then here we have constraints from multi-wavelength cluster surveys. So we're consistent with everyone except for E Rosita. I do have some thoughts on why that might be the case. But yeah, in general, our constraints are consistent with the literature. Okay, so we've done this in Y1. Y3 is something that we're pursuing as well as Decade. But in the future, we want to improve our modeling, specifically to include cross-correlation with galaxies and clustering at the clusters. And so right now, what we are able to do does not include the cross-correlation with galaxies because our HOD mock galaxy catalogs are not very well motivated, and we don't know how to actually deal with the correlation coefficient between the red sequence galaxies we would want to compute the clustering of and the clusters themselves. So the solution is to just generate mocks that we can actually directly run the selection algorithm on, and what that requires then is photometry and colors. And so this is ongoing work led by a University of Arizona undergraduate. And so the idea here is that you can, again, HOD populate a simulation. In this case, it must be a light cone. And the red mapper algorithm actually produces a model of the red sequence as part of its calibration, right? And so what that is basically colors as a function of redshift and also as a function of Z-band magnitude. So you then just have to put the Z-band magnitudes into your simulation, draw the colors from the model that the data produces, and then you have a mock galaxy catalog that you can run the red mapper on, and extra bonus is that you also get red magic selected galaxies out of it. So you have explicitly included all the cross correlations that the selection algorithm introduces. Oh, sorry, that's backwards. Forwards, yes. So I'll just leave you with my summary slide. So we produce this constraint using this forward modeling method, and part of the improvements are being able to go to low richness and small scales. Any questions?
Okay, thank you for keeping your talk within the time, and we have time for questions. Again, Yan Ting first.
Thank you. I'm curious about, so is there any confirmation bias here?
Meaning that we thought there was selection effects, and so we put it in. Is that
also, I'm curious, your abundance matching approach, which is very nice, but you need to introduce any scattering. And if not, why not?
Well, we've tested it and we find it doesn't make a huge difference, but, I mean, we've added extra super Poissonian scattering to the HOD, but you mean to actually scatter the abundances of the, right. Well, I mean, it adds extra freedom, I suppose, but I don't see why it's necessary. But let me actually say, I think the way to address this is to go to your first question about confirmation bias. Right? So, I mean, of course, people produce they produce the blue contour and they immediately try to figure out what had gone wrong, and so selection effects were a possible issue. But there was a lot of work afterwards to understand how the phenomenology of these selection effects in buzzard and some work in cardinal. And so what we've done is completely motivated by that. So, I mean, I don't know. I guess it's for you to decide, right?
Go to the next question.
Yeah, probably related. I mean, maybe what do you think the dominant systematics are to this approach? And yeah, I'm kind of also wondering, related to Linting's question, sort of especially like generating these mock galaxies and like your ability to actively put down mock galaxies on the sims, like. Yeah, are you worried about things like scatter or not recreating like, the galaxy populations down to low enough mass that, you might be like misrepresenting low lambda clusters or something like that?
Right, so as for the freedom in the HOD, we have done some tests. So we have a 4-parameter HOD. Assembly bias is a possibility. There are more like sort of flavors of HOD or extensions to HOD, but a lot of them have to do with the one halo, the distribution of galaxies in the one halo term, which I suspect should not be very important just because the aperture is relatively large compared to the effects of those extensions. And then as far as resolution is concerned, we're going down to 10 to the 11. So we're pretty confident that we're not having issues with resolution. The minimum mass to host the galaxy is well constrained, well above 10 to the 11. So that is a concern though, because when I think I can show the master slides, right? When you look at the implied mass distributions of this selection algorithm, so this is the mass distribution for the richness 20 to 30 galaxies. This is from a previous paper where we assumed quantum cosmology. You do have this long tail down to, in this case, 12.5. But yeah, down to richness 10, we're confident that 10 to 11 is sufficient.
Okay, next question from Chango.
The estimation of omega matter is always smaller than Planck estimation. So if you detect fewer clusters, then are you going to get higher omega matter?
If you detect fewer clusters, would you have higher omega m?
Right, I'm just wondering the direction. So if you detect fewer cluster than what you detect here, then would that push omega matter estimation to a larger value?
I think lower omega m would tend to indicate fewer clusters, but there is a degeneracy with sigma 8 and other parameters, right? There's also degeneracies with baryon effects as well.
Right.
Yeah. There's high order degeneracies, but I would say lower omega m tends to indicate fewer clusters. It's somewhat complicated because it depends on the mass richness relation as well.
I guess lower omega m will give you slow evolution, rest evolution. Mass discrepancy between rest 0 and rest 0.8. Sigma 8 govern the normalization, right? But
So-
omega n changes the evolution speed.
Okay, so you're saying a fixed sigma 8, lower omega m, probably has more clusters at relatively higher redshift.
Right.
I think that's right.
Okay.
Thank you. Amazing results. Can you say more about the projection effect, or how do you deal with it? Do you have the slide there, and how can you model the projection effect such that you can go to the reaching to 10?
Well, the whole purpose of the forward modeling is to capture the projection.
In this approach, you don't need to spatially model, or this is implicitly included.
It's implicitly included, but so I mentioned that there was follow-up work from the Y1 result that looked at projection effects in Mach galaxy catalogs that RedMapper had been run on, and so there the phenomenology was determined to basically be like this cylinder selection, right, where you have to free the depth potentially, but you're not very sensitive to other details. So these are the implied projection effects from the analysis at Planck cosmology. So this is the lensing divided by the lensing given the mass distribution. The points with error bars are the projection effects that come out of Buzzard. It's not expected that they would necessarily agree, but it turns out that they roughly do. And then here's the derived projection effects from the best fit. So you have strong projection effects, in short.
Okay, time's up. Let's thank our speaker one more time.